half an hour, 45 minutes, we're gonna look at the summary. We're gonna summarize everything you must know prior to midterm exam. But prior to that, let's look at a few more details related to this constraint stabilization. Constraint stabilization could be asked in midterm exam in a level that, what's the concept, like why you need it. And you need it because you converted your differential algebraic equation to be ordinary differential equation. And in the course of that transformation, you actually introduce the constraint only in acceleration level. That's the reason why you need this stabilization. Got it? Now, if you heard me like acceleration, stabilization, that's all right, because you still have plenty of time to look at that in lecture notes. And it's not really the core content, so you can live your life fine without knowing that in details. And you can score high from the written exam even if you don't know this in details. Okay, but this goes deep into mathematics, like really how was the mathematics, whatever you learn, the integrals in, I don't know where is that they teaching that, in a junior high school or elementary school, I don't know that. But anyways, when they teach the integration, it tells you that there is this integration constant that comes along. And we haven't discussed about that, and that's exactly the source that's causing this problem, this drifting problem, that the problem that the constraints are no longer fulfilled. Because if you look at, this one here, this equation where constraints are expressed in acceleration level. When you're coming down to velocity level, there is this constant vector that depends on the initial configuration, initial condition. You can kind of guess that, but when you go one step down from that, when you're going to position level, then you will have two constant vectors. And now it becomes difficult to define them. And this is exactly what we are missing. And because we are missing that, we have to find a little bit artificial way to introduce these mathematical mistakes we did in the very beginning when we converted to a set of differential algebraic equation to be ordinary differential equation. Okay, so how is that we can, well, this is just all that thing related to this constant vectors explained. We don't need to repeat that. But what exactly we can do then? Well, we can fix this problem by expressing the constraints a little bit of modified way. And in this little bit of modified way, I still have my acceleration component as it is written here. But then I'm using additional two artificial components that are forcing this equation to fulfill the constraint also in velocity and position level. And these two additional components are this one here, where the velocity of constraints are multiplied by artificial component alpha, and that is multiplied by 2. And then I have here another component where the positions are multiplied by artificial component beta. This is a very often used constraint stabilization method that is called Baumgarten stabilization. You can read the details from the lecture notes, but there is a clear physical interpretation related to this. And the physical interpretation is simply spring and damper. Because when you look at this one here, this is a component that is kind of like a spring that is forcing constraint to go to its original position. So if I would have here, say, a pendulum system, and the pendulum is in this configuration where the revolute joint is no longer fulfilled. What happens is this component associated to this position comes into play, and it is kind of like artificial spring that forces this constraint to fulfill the position level constraint. All right? So it's putting it to its original location such that no violation takes place whatsoever. But you know that spring only will be difficult because that would introduce the vibration. So then the system will vibrate all the time around this correct value. But if I have this component here, this is like a damper. So the damper that is damping down the possible violation of constraint. So the spring and damper altogether forces constraint to go back to the original configuration, and that's when the constraints are fulfilled. And that's what is called constraint stabilization. So I'm stabilizing the mistake that I did when I introduced this constraint only in acceleration level. Is anyone doing this? No one. So it's like, so would you like me to repeat it? Hell no. Yes. Okay, so let me repeat this in short. Okay, so whole story in a nutshell is this. You know, everything started here. So let me go back here. And let me erase this. Okay, so we started from the set of differential algebraic equations. Everything was fine in this point. But then I say, let's convert this to be set of ordinary differential equations. And we made it happen. But we made it happen in a way that was not correct, I mean mathematically not exactly correct. Because what I did was that I simply introduced the constraint here in acceleration level, not position level that they are originally defined. You know, you can see the difference here. So this is position level, this is acceleration level. So there are different levels. Now what happens when I do my integration, I'm always introducing certain amount of errors. Always that happens. I just cannot be exact. And now when that happens, it's possible that the constraints are no longer fulfilled here in the position level where they were originally intended to be fulfilled. All right? So how can I fix this problem? Well, I can fix this problem by introducing two artificial components that are such the way that they have physical interpretation as a spring and damper. And they forcing constraint to be fulfilled not just only in the acceleration level, but also in a velocity and position level. And now life is good. So I'm good to go. So I'm not introducing any more errors because of my constraint fulfillment. Make sense? Now you can do this because your fellow student is doing this, so you need to look smart and doing this. Even though that inside of your head you're like, oh my God, so this is painful like in hell. But still, you know, this is in a nutshell how it goes. But again, like I explained just prior to break, not the core content of this course. Something that if you're scoring high, if you want to score high, you have to know these two. Are you planning to score high? Yes, because of can-do attitude. So it's simple like that. Okay, so let's go. So then finally, here's a list. Here's a list that you have to know. And now, let me explain you something. This is really the list that you need to look at. But if you are really feeling that I am an outstanding student and I need to show off, I really need to, you know, I have to get 5 out of 5 from this exam. Nothing else is satisfying. If that's the case, then you also need to look at the lecture notes because there are certain topics only mentioned in lecture notes. And it's possible that I can ask something from those subject matters as well. Let me give you an example. You know, here's a lecture note. Now let me go to the table of content. So everything pretty much is clear here, so it's not anything too difficult, but like here, parallel axis theorem. Actually, it sounds really sophisticated. It's a very simple thing to read. So if you wanted to score high, you need to also to study these minor details that I mentioned in the lecture note. But here comes the good news. I am not expecting you to read any other material except the slides that are in here in the lecture and also the lecture notes. And now if you're aiming to score good number, it could be even 5 out of 5, still is possible to neglect some of the topics that I mentioned here in the lecture notes, like again, parallel axis theorem, not necessary to do that. But everything that I have explained here, you have to be sure that you master all the details related to those subject matters. Sounds fair? So I'm not expecting you to go and purchase a book and read something from the book. Everything is in Moodle database. Everything is in my lectures. Everything is in our recordings. So go ahead and start looking the recordings over and over again until you're sure that you have full knowledge. And also make sure that you understand the details that are mentioned here in the lecture notes. But if you need to make a selection, take a look at the PowerPoint slides and recordings only. That's my advice to you. But pretty much everything that is explained in the lecture notes is also explaining my lectures. But finally, how is your ratings? How are the different topics? So the first one is a description of planet body. Now, something that I desperately would like you to understand is that particles don't have a rotational degrees of freedom. This is very confusing, and it's not simple to understand that, because we kind of have the rotational degrees of freedom and then we don't. So what is this? So how is it even possible that we have and then we don't? Let me explain it. You know, the big picture we have in the multi-body dynamics is that we wanted to describe a particle. An example is the one that is in a red font here in a picture. With respect to global coordinate system, that's really the ultimate call we have. So this point here with respect to this coordinate system. And now comes something that is extremely important. This point that is mathematically called as a particle that do not have rotational degrees of freedom because it's very small. It is so small that you don't see, if you rotate it a little bit, you cannot recognize it. Not even using a microscope. You just cannot recognize it. So where this rotational degrees of freedom then comes into play? It comes in a way play because we have a certain way to describe this particle with respect to global coordinate system. How is this way? The way goes such the way that we can introduce additional coordinate system, which is like assisting coordinate system. And this assisting coordinate system is called body reference coordinate system. Body reference coordinate system is attached to body. So if body translate, the coordinates moves along, and if it rotates, the coordinate system moves along. So it's attached to body. You cannot separate those two things anymore. And now, how can I describe this particle? I'm going to describe that with help of my body reference coordinate system. First, I'm going to travel from my global coordinate system to origin of my body reference coordinate system. How can I express that in planar case? That will be vector r that consists of two components. All right? And then I'm going to count the orientation of body reference coordinate system with help of 2x2 rotation matrix. That's where the rotation comes into play. So it is because of this assisting coordinate system. But I'm still not describing the rotation of particle, but I'm just using this additional information to make it easier to describe that particle, nothing else. Clear? Okay? So then the vector u bar, that's the one that is constant, and that's the one that describes the particle within the boundaries of the body. So that's how it goes. That's the one that I'm expecting you to know, 5 stars. So this is the highest possible rating, highest. So make sure you know this. Spatial body, less important. Starting, they say the rating is 3 star, so it's not that important. It's not that difficult because, only difference is that I have here a little more dimension in my translational components. So instead of using 2, I'm using 3. And instead of using here 2x2 rotation matrix, I'm using 3x3 rotation matrix. Description of that 3x3 rotation matrix, that though is complicated. And we learned one way to do it, which was based on Euler angles, and we're going to look at the Euler angles in a second. These two here is a vector u bar that consists of 3 components. one more thing, by the way, and this is something that you can find in an exam, is that, rotation matrix that is used in planar and spatial cases, 2 and 3 dimensional cases, those are mathematically orthogonal, meaning that if you're forming a vector, 2 vectors from the columns of the rotation matrix, these 2 vectors will be perpendicular with respect to each other. 90 degrees angle with respect to those 2 vectors. All right? So if you're going to make a vector out of this, so it's going to point in this direction, vector out of this is going to point in this direction, and it's going to be 90 degrees angle, meaning it's perpendicular with respect to each other. Okay, so and also they're unit in length, but orthogonality means that they are perpendicular with respect to each other. Okay, so then that's a spatial body. Euler angles are not even rated because it's that they are part of the spatial body. So we learned that there's a way to describe the orientation in 3-dimensional space by using 3 successive rotations. And this successive rotation takes, first place around z-axis, then x-axis, not the other way around, and then z-axis. So it's 3-1-3 rotation sequence. And you can describe each one of these rotations by using 3x3 rotation matrix. And when you're multiplying them together, then you're going to get this 3x3 rotation matrix as it is written here. Please don't try to memorize this. For sure, I'm not going to ask anything like that. And why would I? Because you have your lecture notes with you when you do your exam, so it makes no sense. So don't try to memorize anything like that, but memorize the concept. So it's based on successive rotations. And, usual sequence that is used is 3-1-3, Z, X, Z. Could be other thing as well, but that's the most often used sequence. Clear? Okay, so let's move on. Description of velocity. This is, remember, this is really the everything where everything can be derived from. And now what I did when I describing the velocity was that I differentiate this equation with respect to time. And when doing so, you're going to get 2 components. Oh, well, that was nice. Okay, so the 2 components that are translational velocity and then angular velocity. And this is how you can describe the angular velocity. And this one here was a rotation matrix that is differentiated with respect to angle theta. Nothing else. Again, it's more like good to know level. Then acceleration, 2 stars only. So skip it if you don't have much time to invest to this midterm exam. Now once you differentiate your velocity one more time with respect to time, you will get your acceleration, which consists of translational acceleration component, normal acceleration component, and tangential acceleration component. And this already tells you that your inertial forces will be linearly related to acceleration and quadratically related to velocities. Because how is an acceleration? Simple like that. Okay, so let's move on. So let's look at the other stuff. So tenorized coordinates, look at that. So it's a 5 star, so it's rated as a 5 star, so it's a very high importance. So again, what are the tenorized coordinates? Those are the one that is defining your configuration, is defining the multi-body configuration. So one body in planar case must have 3 tenorized coordinates because when you look at this equation that we use to describe the kinematics, 2 components associated to translation, they can be variable. They can change their numerical values when the body translates to X and Y direction. And also this one here, which is a rotation matrix, can change its numerical values because of the body rotation. So that in total is 3 tenorized coordinates that are Rx, Ry, and angle theta. That's something that is extremely important to understand, because that's what we're going to use later to express all the forces with respect to generalized coordinates. Okay, then constraint equation, equally important. By the way, look at that. So there may be questions that are related to, please compute the number of degrees of freedom. And then don't think about anything like shortcut, just compute the number of generalized coordinates and also compute the number of constraint equations. So this is a number of generalized coordinates, this is a number of constraint equation, and do the math. Simple like that. Now we can have 3 different scenarios based on the number of degrees of freedom. We can have a dynamic system, which means that the number of degrees of freedom is 1 or higher. So this is integer number. So it can be 1 or higher, meaning that system is actuated by forces. So in order to compute the response, you must have equation of motion. That's first scenario. Second scenario, that the number of degrees of freedom is equal to 0. No need to compute the equation of motion, because you can solve the response using kinematic analysis. Just kinematic, nothing else. Because everything is defined by constraints. So no need to express the equation of motion, but simply use the kinematic analysis. This is something that very high, there is a likely that I'm asking something like that in written exam. And then the final scenario is over constraint system, which is unable to move. But don't mix the over constraint system to redundant system. Remember, the redundant system is something that constraints are not independent, but they are constraining the same generalized coordinates, and they can be, they should be eliminated from the system. Meaning that you have like pendulum body here, and you have one revolution here, and exactly same place you have another revolution. So it's not that you have 4 constraint equations, because they are not independent, but they are placed in the same location, and they limiting the motion possibilities exactly same way. So they are not independent, but they depend on each other. Okay? So that's a typical example about the redundant system. Clear? Would you like to discuss about something? So far, all good. Is it? Okay, let's go. Oh, what is that? Well, that's, if their maximum is 5, how many we have here? I cannot even count that far. Is it 10 or what? So is it like super important to learn this? So what is this super important to learn? This is that Jacobian matrix, which, is a good friend of us. So it's nothing to be worried about. But what is that we have to have? What are the ingredients? What are the components that you must have in order to build the Jacobian matrix? You must know your vector of constraint equations. So you have to have your constraint equations, and you have to have your vector of generalized coordinates. When you're putting those 2 things together, that's going to be Jacobian matrix. How is that you're putting them together? That will be based on partial differentiation. Okay? So, this is a vector of constraint equation, this is a vector of generalized coordinates. And once you're using this partial differentiation procedure, you can get your Jacobian matrix with nothing. Makes sense? Practice this. Practice this in a system that consists of, say, 2 bodies. I would say that's the good way to practice it. Test yourself in a system that you can make like mechanisms that are constrained to ground by a revolution here, and then there may be another body like this, and there may be a primitive joint in the middle here, something like that. Test it if you can build it, and that's the good way to practice the midterm exam. Make sense? You still have the can-do attitude, or you still have it? Good. Let's move on. Kinematic analysis. So it's rated, this is like I said that, some of the things are rated low. Not many things are rated low. So because pretty much everything are like 4-star, sometimes 10 stars. 10 is exceptional case. But this is something that, remember again, that position level analysis in kinematics is based on iterative process. So it's not that you can get the solution automatically, but you can get Newton difference. And the Newton difference is the one that is expressed here. And with help of Newton difference, you can update your generalized coordinates in order to make them to be more closer to your final destination. Final destination here means whatever fulfills the constraint at any given time. Okay? Then velocity level is a pure substitution thing. So you just substitute your information, that's it. And acceleration is same thing, it's just more painful, but other than that, substitution. Okay? So we're gonna continue because there is this surprise in-class quiz, actually 2 of them. So now I hopefully that you were listening to me when I was explaining about this the transformation matrix and how these vectors are perpendicular with respect to each other. Orthogonality condition, because that's what I'm gonna ask within a few minutes. So I'm asking what it means to have an orthogonality condition. Is it true or false that then the vectors are having 90 degrees angle with respect to each other? Put that in your mind because I'm coming back to that soon. And then also I'm going to ask, what's the physical interpretation of Lagrange multipliers? You still remember that? Reaction forces due to the constraints. Okay, but now this. So generalized forces, principle of virtual work, rated as 3 stars. So not necessary to be a master of this topic if you want to score, say, 2 out of 5. You can skip this. Now, so how it goes, you have here virtual work done by externally applied forces. And by the way, why you do this? What's the big picture behind? The big picture behind is that you want to convert force to be expressed from global coordinates to be expressed by using generalized coordinates. Global coordinates you have 2, generalized coordinates you have 3 per body. That's matching, or this mapping can be expressed with help of virtual work and virtual displacement in details. Now, this delta R can be expressed as delta Q, and the mapping matrix you need, that's the one that is shown here. So that's the one that converts something that is expressed from global coordinates to be expressed by using generalized coordinates. That's how it goes. So now once you do this conversion, then your forces will be expressed by using generalized coordinates, and that's how you can actually make that happen. So that's the details in that procedure. And then the same thing for generalized inertia forces. They are rated a bit higher than the external applied forces as 4 stars. Now, you just take your expression of acceleration, which is shown here, and then you take this previously defined mapping matrix, and you're expressing your acceleration to be expressed by using generalized coordinates. Look at that. So here's the acceleration is expressed by using global coordinates. No good. I cannot use that because I want everything to be expressed by using generalized coordinates. And now that trick can be made with help of this mapping matrix. So once substituting everything here, then you will get mass multiplied by acceleration and quadratic velocity vector. Mass matrix, that's the one that consists of 3 different components. And remember, it is a diagonal representation if body reference coordinate system is located in the center of the mass. So first component, which is a 2 by 2 matrix that is located here in the upper left corner, and mass of the body is located in a diagonal component. Rest is equal to 0. Then my final component, or my second component, is mass moment of inertia. It is associated to translational generalized coordinates only, nothing else. And then something that combines the translation and rotation is this one, no clear physical interpretation, and that's the one that becomes equal to 0 if your body coordinate system is located in the center of the mass. So you do this. Good. All right, the quadratic velocity vector, look at the ratings. 2 stars. You can skip it if you're in a hurry. Now, what it means, well, you know how you can compute it. The details are explained here, but this comes together with this part of the mass matrix. So if this part of the mass matrix is non-zero, then the quadratic velocity vector will be non-zero. And what it's actually doing, it is actually accounting the centrifugal forces due to the rotation. Now, if your body reference coordinate system is located in a center of mass, and you're rotating your system here, no centrifugal forces takes place that is applying your body reference coordinate system. So that's why it becomes equal to 0. If it is located in a one end here, yeah, then it takes a place. And how much it's going to be, it depends how far off is your body reference coordinate system. Okay? How many formulas? 5 stars. So, here, what is very important to know, what is the role of this component? Again, Lagrange multipliers are reaction forces due to constraints. This one here is generalized inertia forces, and it consists of 2 components, mass multiplied by acceleration and quadratic velocity vector. The externally applied forces is here, and this is the one that you can now set to be equal to 0, and with help of constraint equation you can solve the whole thing. Okay. Now, let's look at the details. So how it goes then. So in exam, so this is directly copied from the Moodle database. It's not yet visible for you, but it will be soon. So it will be visible for you sometimes this week, and you are allowed to get started Sunday at right after midnight. So it's actually 1 minute after midnight you're good to go. So you can make your first attempt. And then it's going to be closed just before the midnight. Now I'm not sure if you open your exam just before the midnight, if you are still able to complete it. That I'm not sure. So it's better to be safe and start at, say, at 10 at latest. That's my recommendation. Okay, time limit, 2 hours. So you have 2 hours time to do it, and the grading method is highest will account. 2 attempts. Highly recommended to actually do those 2 attempts. And again, my recommendation, make your first attempt on Monday to see how is your level of knowledge, to get the picture like how much you actually need to work, how much more you need to work. And then you can make your final attempt sometimes during the weekend. How that sounds? How many points? That's we're still counting that. You know, there's a little bit of instructions that you should read prior to clicking that yes, go ahead and start the exam, because once you click that, that's it. You cannot anymore escape from that. You can, however, go back to different questions and modify your answers as many times you want. The last answer will be the only one that will be accounted. So if you later, during the course of the exam, you get an idea that, you know, what I answered in the beginning was incorrect, you could just go and modify it. You can modify it as many times you want. Okay. Can we make an attempt? Can we try to see like how good you would scoring from the exam? Yes, sir.
How many questions you said last week you will tell? How many questions?
I cannot tell you that. It's usually, but it's going to be written to you. So once you log into that exam site, it tells you what's the maximum point, how many different questions. So it will be, but we're still defining the exam because we wanted to make it more difficult than usually. So that's the reason. Yes, sir.
Do we get the answer right after submitting?
Yes. No. Yes and no. So you can get. Yeah, that's a good question, by the way. You will get your scoring, but not the correct answers. Because what we're doing is that we have a question bank. So we have a little less than 1 million different questions that are related to subject matter, and then there's a lottery machine that is, giving you the questions. So it's at least theoretically it's possible that you get exactly same question in your next attempt, theoretically. And now if you know it already, then it makes no sense. So we're gonna provide the answers to you later once the whole exam is closed. So that's gonna be Monday morning. I mean, not the Monday morning when you started, but Monday morning afterwards. So then you're gonna learn it. But important that you get your scoring automatically. Because if you got a score 5 out of 5, that's it. No second attempt is not needed. Yes?
Are there like some kind of multiple choice questions, or do we need to use a math tool?
Yes.
Yes, to which one?
Both. Yes. So it's always yes.
Is there a need to submit any kind of files?
No files. No files. So everything you need. Okay, what is the tool you need? You need to have a browser and a solid internet connection. And then you can use whatever you want, except your fellow students, and except your mom and dad. You cannot use any external help. We reserve to have a right to invite some of you to have an oral exam. That's what we do. So even the online participants, we can call you. And then it's going to be a oral exam. And if you fail, that's bad. Yes, sir.
Well, tell us which one we got wrong.
So which one is?
Like on the online exam, well, tell us which one we got incorrect.
So in online exam, I'm not hearing you well. So you're asking.
Like when you take the exam, I'll show you the score afterwards, but we'll show you which ones were incorrect.
No, we don't tell you that. So the question was that, yes, we're going to give you the score, but we are not telling which was the incorrect answer. Now, the problem we have in this exam is that there's a little bit of black and white, so quite a bit of black and white. So we're still introducing some systems that if you enter your answer incorrectly, we're saying that is incorrect. So there's something wrong here. Please rethink it. Not sure if we are able to do it this year or not. And if we are able to do it, then it means that we are no longer giving you the full points, but we're reducing the maximum points. But you will have another attempt to that particular question. The problem in online exam that is very black and white. You either scoring full points or you're scoring 0 points. And that's what bothers us a little bit. So we are introducing these systems that helping you and is making a little bit of other colors and just black and white. Yep.
And dive into the water.
Yep. Yep.
Not expect to come out, then prepare for 7 days and then
Sure. That's how it goes. Then you study like in no limit, next 7 days, and you make your second attempt. Maybe if I can recommend, study before the first attempt, at least a little. Because if you just jump in a cold water, maybe it's gonna be too hard. Okay, so let's see. So I have 2 questions that are typical questions that you can find in exam. So you're ready to see how is that you're scoring. My first question is this. If, look at this is very theoretical question. So if A is an orthogonal matrix, then matrix transpose multiplied by original matrix and other way around is equal than identity matrix. This holds that I'm saying. However, it is not necessary that vectors made out of the columns of matrix A will be perpendicular with respect to each other. True or false? No. You're gonna go to in-class quizzes and enter your answer, and then we see how is this how it's going to be. Okay. Two options. Hold on. Go back here. True or false. This is, by the way, typical question. There are a few cases where we're asking true or false. Now the problem is that everything is kind of explained in a lecture note, but you can get an idea that if you don't know the answer, it is too late to open the lecture notes, because it's going to take a little while to understand this concept, and it's going to take too much time that you can complete the exam within 2 hours. Okay? Then I have another question. You can take a look at that too. Physical interpretation of Lagrange multipliers. What a big surprise. So this came right out of the blue sky, so no idea. But options are force is due to the inertia, acceleration of generalized coordinates, rotation of a particle. Let me read it again. Rotation of a particle. And then reaction force is due to the constraints. One only is correct. Okay, so let me take a look. Are we done with the first one? Well, we are not yet done. So what is that you saying? How much is a success rate in this case? 98, yeah, that's a good guess. I would say pretty much the same, roughly that neighborhood. Yeah, 50, 60, roughly that much. Okay, you guys all done with this? No. Oh, so yeah, the problem is that you're sitting close to me. So, you know, when you're close to me, the outer arm is not cooperating. So it's me. For some reason here in the front of the lecture room, the outer arm is very weak. I don't get it, like, why is that? But it's just very weak. Okay? You done? Still, you need to go all the way up. Others, are you done? Okay, so you can think about while we're still struggling with the technical difficulties, think about this. So what is the correct answer for the second one? Again, typical question you can find in midterm exam. Is it cooperating with you? Good? Okay, so then I'm gonna close this. Okay, 95 students. And the success rate is, what was it? 90? 98. Oh my God, I made a mistake, so I need to go back. Here. Okay, so what is, how it goes, then let me go back here. So this perpendicular condition is everything in this orthogonality. So orthogonality means that the vectors will be perpendicular with respect to each other. That's what it is. But the tricky question, I have to admit that. So it's not that simple. So you need to be careful and you need to read it carefully. Then the next one. Here. Okay. So this is the last one. This is the last one for today. And I can see that it's already 6 o'clock. So physical interpretation of Lagrange multipliers. And now I am thinking that it's going to be, yes, 100%. You agree with me? %. So what is that Team Rosser is thinking? Is it going to be 100%? No way. Why is that you guys don't have this can-do attitude? Of course it's going to be 100%. Of course. So what was the number? How many answers was in a previous case? I think it was like 86, something like that. So are you guys all done? You all done? Okay. Oh, so it's 80, 90. 90. Oh, okay. So is it 100%? Yes, it's going to be. Okay, ready? In 5, in 4. Let me just look at that because I'm feeling very good. I'm feeling really good inside of my body. But good news, good news. Only 1%. Only 1%. 1%. But others, it doesn't matter. It doesn't make that much a difference. But 1% is only saying rotation of a particle. And I'm kind of sensing that you guys are doing this intentionally. Okay. So we don't see anymore, but I mean, we're going to see why that thing, camera. The rest we're going to see on, but look, hey, one more thing. So the next semester or next period, the lectures are in a very unusual time. They are no longer in this particular time slot, but they are changing pretty much every week. So take a look at the calendar and make sure that you are watching streaming on time. Okay, thank you.